The Event Horizon Telescope captured more than just the first image of a black hole. Hidden in the data from Sagittarius A star, the supermassive black hole at our galaxy's center, astronomers discovered something that challenges current models of how magnetic fields should behave around such objects. The magnetic field lines show geometric patterns precise, repeating structures that resemble engineered configurations rather than the chaotic tangles predicted by computer simulations. Dr. Elena Vasquez, a plasma physicist at the Max Planck Institute, first noticed the anomaly while analyzing polarization data from the galactic center. The magnetic field topology displays characteristics that are unexpected, she explains carefully. We observe organized, almost crystalline arrangements of field lines extending outward from Sagittarius A star in patterns that our current magnetohydrodynamic models do not predict. The level of organization suggests influences beyond natural accretion processes. These patterns are not random artifacts of data processing. Multiple independent observations using different telescopes and techniques have confirmed their existence. The magnetic structures extend for light years around our galactic center, forming what appears to be a vast network of organized energy conduits. The geometry is so precise that some researchers have begun asking whether these configurations could have been deliberately created. The implications become more intriguing when we consider the age of our galaxy. The Milky Way formed approximately 13.6 billion years ago, less than 200 million years after the Big Bang itself. For comparison, Earth is only 4.5 billion years old, and complex life has existed here for perhaps 600 million years. This means our galaxy has had over 9 billion years to develop intelligent life before our solar system even existed. Professor James Chun, an astrogeologist studying galactic evolution, puts this time frame in perspective. If intelligent life emerged anywhere in our galaxy even half the time it took to develop on Earth, they would have had a head start of billions of years, he notes. The technological gap between such a civilization and ourselves would be comparable to the gap between humans and bacteria. We would be dealing with capabilities so advanced that their engineering projects might be indistinguishable from natural phenomena. This perspective gains credibility when we examine the galactic habitable zone, the region around our galaxy's center where conditions are optimal for the development of complex life. Unlike planetary habitable zones, which depend on distance from a star, galactic habitability depends on factors like stellar density, heavy element abundance, and protection from cosmic radiation. The zone extends from roughly 13,000 to 33,000 light-years from the galactic center, a vast region containing billions of potentially habitable star systems. Recent analysis of stellar metallicity data shows that this habitable zone became conducive to complex chemistry much earlier than previously thought. Dr. Maria Rodriguez, an astrochemist at the European Southern Observatory, has traced the evolution of heavy elements throughout galactic history. Our models indicate that sufficient carbon, oxygen, and silicon for complex chemistry existed in the galactic habitable zone over 10 billion years ago, she explains. This pushes back the potential emergence of technological civilizations by several billion years compared to our own development timeline. The magnetic field patterns around Sagittarius A star become even more significant when viewed in this context. If ancient civilizations did achieve technological maturity billions of years ago, they would face the same question that confronts any sufficiently advanced species: how to harness the enormous energies available at galactic scales. Black holes represent the most concentrated energy sources in the universe, capable of powering civilizations for trillions of years through various extraction mechanisms. The concept of black hole engineering is not science fiction but legitimate theoretical physics. Roger Penrose proposed the Penrose process in 1969, demonstrating how energy could be extracted from a rotating black hole by dropping material into the ergosphere, the region outside the event horizon where spacetime itself is dragged around by the black hole's rotation. More recently, physicists have explored concepts like Dyson spheres around black holes and magnetic field manipulation for energy extraction. Dr. Sarah Kim, a theoretical physicist studying black hole thermodynamics, describes the possibilities. A sufficiently advanced civilization could manipulate the magnetic field structure around a supermassive black hole to extract rotational energy with extraordinary efficiency, she explains. The organized field patterns we observe around Sagittarius A* are consistent with what we might expect from such large-scale engineering projects. The magnetic configuration could function as a galaxy-spanning power grid. But energy extraction is only one possibility. Advanced civilizations might engineer black hole magnetic fields for communication, computation, or even space-time manipulation. The field structures could serve as vast information processing networks, using the extreme gravitational environment to perform calculations impossible with conventional technology. They might also function as galactic-scale communication systems, modulating magnetic field patterns to transmit information across interstellar distances. The precision of the observed magnetic geometries suggests sophisticated control mechanisms. Natural astrophysical processes typically produce chaotic, turbulent magnetic fields that change rapidly over time. The organized patterns around Sagittarius A* remain stable over observational timescales of years to decades, implying active maintenance and control. This stability is unexpected given the violent environment near a supermassive black hole, where matter reaches temperatures of billions of degrees and travels at significant fractions of light speed. Professor David Torres, an expert in magnetohydrodynamics, has been modeling these field configurations for the past 3 years. The mathematical description of these magnetic structures requires terms that do not appear in natural plasma physics, he notes. We need to invoke external organizing influences to reproduce the observed geometries. The question is whether these influences represent unknown physical processes or technological intervention by intelligence operating at galactic scales. Independent evidence for ancient galactic engineering may exist in other observations of our galaxy structure. The Fermi bubbles, discovered in 2010, are enormous gamma-ray emitting structures extending 50,000 light-years above and below the galactic plane. While mainstream astronomy attributes them to past activity from Sagittarius A*, their precise geometry and longevity challenge natural formation models. The bubbles show sharp boundaries and uniform internal structure that are difficult to explain through conventional astrophysical processes. Dr. Jennifer Walsh, who studies high-energy phenomena in galactic cores, describes the puzzle. The Fermi bubbles display characteristics that are inconsistent with explosion or outflow models, she explains. Their edges are too sharp, their structure too uniform, and their longevity too great for natural formation mechanisms. They appear more like constructed objects than the remnants of astrophysical events. We may be looking at the remnants of massive engineering projects undertaken millions of years ago. The bubbles contain another anomaly. Their gamma-ray emission spectrum includes narrow spectral lines that do not match known astrophysical processes. These lines suggest specific nuclear reactions or particle interactions that would not occur naturally in the galactic environment. Some researchers have proposed that the emission signatures could result from exotic matter interactions or controlled fusion processes operating on scales vastly larger than anything achievable with current human technology. Analysis of the bubble structures reveals internal organization that extends down to parsec scales, regions roughly the size of our local stellar neighborhood. Within the overall bubble structure, astronomers have identified filamentary networks, void regions, and density variations that form geometric patterns. These substructures maintain their organization despite the turbulent galactic environment, suggesting either remarkable stability in natural processes or ongoing maintenance by technological systems. The implications extend beyond our own galaxy. If intelligence can emerge and persist for billions of years, then advanced civilizations should be common throughout the universe. The fact that we do not observe obvious signs of such civilizations, known as the Fermi paradox, might simply reflect our limited understanding of how galactic-scale engineering would appear to a young technological species like ourselves. Dr. Michael Santos, who studies the statistical likelihood of extraterrestrial intelligence, offers this perspective. We have been searching for signals and artifacts that resemble our own technology, scaled up by orders of magnitude, he explains. But civilizations with billions of years of development would likely employ principles and technologies we have not yet discovered. Their engineering projects might be invisible to us or appear as natural phenomena that we have not learned to recognize as artificial. This possibility transforms how we interpret other mysterious galactic phenomena. Fast radio bursts, originally thought to be natural cosmic events, show precise timing and frequency patterns that some researchers now consider potentially artificial. Pulsars, though clearly natural objects, emit signals so regular that they were initially mistaken for alien beacons. If advanced civilizations exist, they might utilize or modify such natural phenomena for their own purposes, creating hybrid natural-artificial systems that challenge our ability to distinguish between intelligence and physics. The search for galactic intelligence requires expanding our definitions of what constitutes evidence of technological activity. Rather than looking for radio signals or obvious megastructures, we might need to examine the large-scale organization of galactic phenomena for signs of purposeful design. This approach, known as galactic archaeology, seeks to identify patterns in cosmic structure that could result from engineering projects operating over geological timescales. Recent advances in computational cosmology have made such analysis possible. Supercomputer simulations can now model galactic evolution over billions of years with sufficient resolution to distinguish between natural and potentially artificial development patterns. These models provide templates for what galaxies should look like if they develop purely through natural processes, allowing researchers to identify anomalies that might indicate technological intervention. Preliminary results from these studies are intriguing. Several aspects of our galaxy's structure deviate from the predictions of pure natural evolution models. The distribution of heavy elements, the organization of stellar populations, and the dynamics of gas flows all show subtle but persistent differences from simulated natural galaxies. While these deviations could result from unknown astrophysical processes, they are also consistent with large-scale modification by intelligence operating over cosmic timescales. Professor Lisa Chun, who directs computational galaxy modeling at the Institute for Advanced Study, describes the challenge. We are essentially trying to detect the fingerprints of intelligence in systems so vast and ancient that the engineering projects themselves might span millions of generations of any civilization undertaking them, she explains. The signatures we seek would be subtle modifications to galactic structure accumulated over billions of years. We are looking for evidence of intelligence that thinks and acts on timescales comparable to stellar evolution itself. As we delve deeper into this investigation, we must confront fundamental questions about the nature of intelligence and its potential manifestations at cosmic scales. The magnetic patterns around Sagittarius A star and the organized structures of the Fermi bubbles may represent our first glimpse of galactic engineering technology so advanced and so ancient that we are only beginning to recognize it as artificial. The evidence suggests that we may not be alone in our galaxy, and we may not even be the first intelligent species to call it home. Instead, we might be the latest additions to a cosmic community that has been shaping our galactic environment for billions of years before our planet even existed. Deep within the galactic halo, astronomers have discovered something that challenges fundamental assumptions about how galaxies form and evolve. Networks of dark matter filaments connect distant star clusters in patterns that show geometric regularity extending across thousands of light years. These structures, initially dismissed as observational artifacts, display organizational principles that do not emerge from gravitational collapse alone. They appear to have been shaped by processes that operate according to mathematical rules rather than chaotic gravitational dynamics. Dr. Rachel Martinez, a cosmologist studying large-scale structure formation, first identified these patterns while analyzing data from the Gaia Space Telescope. The dark matter scaffolding shows topology that resembles engineered networks rather than natural clustering, she explains. We observe nodes, connections, and hierarchical organization that would be expected from design systems but not from gravitational assembly. The patterns suggest information processing or resource distribution networks operating at galactic scales. To understand the significance of this discovery, we must consider what advanced civilizations might actually do if they had billions of years to develop technology. While science fiction often envisions alien worlds and space fleets, the reality of galactic-scale intelligence might be far more subtle and far more profound. Civilizations that persist for cosmological timescales would likely focus on fundamental problems: energy harvesting, information processing, and perhaps most importantly, ensuring their own long-term survival against cosmic threats. The energy requirements alone point toward black hole engineering. Professor Alan Singh, who studies the theoretical limits of energy extraction from black holes, calculates that a single supermassive black hole could power a galactic civilization for trillions of years. Sagittarius A star contains approximately 4 million solar masses of material, representing an energy reservoir equivalent to converting the entire mass of 4 million suns directly into usable power, he explains. Even with conservative extraction efficiencies, this represents energy resources that dwarf stellar output by factors of billions. But the magnetic field patterns around our galactic center suggest more than simple energy extraction. The geometric configurations bear resemblance to theoretical designs for black hole computers, systems that use the extreme gravitational environment near event horizons to perform calculations impossible with conventional physics. In these systems, information processing occurs at speeds approaching the fundamental limits imposed by quantum mechanics and relativity. Dr. Sarah Kim, whose research focuses on computation in extreme gravitational environments, describes the possibilities. Near a black hole, time dilation effects mean that vast amounts of computational work can be accomplished in the outside universe's timeframe while using relatively little energy, she explains. A sufficiently advanced civilization could construct distributed computing networks using the space-time curvature around multiple black holes. The magnetic field patterns we observe could represent data pathways in such a system. The implications become staggering when we consider the processing power available. Conservative estimates suggest that a black hole computer utilizing Sagittarius A star could perform calculations equivalent to all human computational work throughout history in less than a microsecond. Such systems could simulate entire universes, model complex evolutionary scenarios, or solve mathematical problems that would require conventional computers longer than the age of the universe to complete. But what would galactic-scale intelligence actually compute? The answer might lie in the very survival challenges that any long-lived civilization must confront. Over billions of years, advanced species would face cosmic catastrophes that could threaten their existence. Gamma-ray bursts, stellar collisions, galactic mergers, and eventually the heat death of the universe itself. Preventing or surviving such events would require predictive modeling on scales that encompass entire galaxies and timespans measured in cosmological epochs. Professor David Chun, who studies catastrophic risks in astrobiology, outlines the challenges. A civilization that wishes to survive for cosmological timescales must essentially become a galaxy management system, he explains. They would need to monitor stellar evolution, predict and prevent collision events, manage energy flows, and potentially even modify the large-scale structure of their galactic environment. This would require computational resources and engineering capabilities that operate at the scale of the galaxy itself. This perspective transforms our interpretation of galactic structure. Features that astronomers attribute to natural processes might actually represent the accumulated effects of billions of years of cosmic engineering. The spiral arms of our galaxy, for instance, show surprising stability over cosmological timescales, a characteristic that challenges purely gravitational models of galactic dynamics. Recent simulations by Dr. Elena Torres at the Institute for Theoretical Astrophysics suggest that maintaining stable spiral structure requires active intervention. Natural galactic evolution tends toward more chaotic configurations over time, she notes. The persistence of our galaxy's spiral pattern implies ongoing organizational processes that counteract gravitational disruption. These could be natural density wave mechanisms, but they could also represent large-scale management by intelligence that has learned to maintain galactic architecture. The Fermi bubbles provide another example of potentially artificial galactic modification. These enormous structures show characteristics that challenge natural formation models but make sense as products of deliberate engineering. Their sharp boundaries, uniform internal structure, and longevity suggest active maintenance rather than passive evolution. Moreover, their positioning and geometry would be optimal for several theoretical applications that advanced civilizations might pursue. Dr. Jennifer Walsh has been studying the possible functions of bubble-like structures in galactic engineering scenarios. These formations could serve multiple purposes for a galactic civilization, she explains. They could function as radiation shields, protecting inhabited regions from cosmic ray bombardment. They could serve as communication networks, using gamma-ray emissions to transmit information across interstellar distances. Or they could represent waste heat disposal systems for massive computational or industrial operations. The energy requirements for creating and maintaining the Fermi bubbles align with what we might expect from black hole engineering projects. The total energy content of the structures equals approximately 10 to the 55th power joules, equivalent to converting roughly 1,000 solar masses directly into energy. This enormous energy output could be readily supplied by a Penrose process extraction system operating around Sagittarius A star over timescales of millions of years. But the most intriguing possibility is that the bubbles represent deliberate galactic terraforming. Advanced civilizations might modify galactic environments to make them more suitable for life or to protect existing inhabited systems from cosmic threats. The Fermi bubbles could function as part of a galaxy-wide life support system, regulating radiation environments and managing the flow of matter and energy through galactic space. Professor Michael Santos, who studies the evolution of intelligence over cosmic timescales, describes this scenario. Sufficiently advanced civilizations would not simply adapt to their galactic environment but would actively modify it to suit their needs, he explains. Over billions of years, such modifications could accumulate to the point where the entire galaxy becomes essentially an artifact, a carefully managed system optimized for the flourishing of intelligence and life. We might be living inside such a system without recognizing it. This possibility gains support from observations of other galaxies. Comparative studies show that the Milky Way exhibits several unusual characteristics that distinguish it from similar spiral galaxies. Our galaxy shows exceptional chemical homogeneity, with heavy elements distributed more uniformly than gravitational models predict. We also observe anomalously low levels of certain types of stellar formation activity that typically characterize galaxies of our size and age. Dr. Lisa Rodriguez, who conducts comparative galactic studies, finds these differences significant. The Milky Way appears to have been managed in ways that optimize conditions for complex chemistry and stable planetary systems, she notes. The distribution of heavy elements, the regulation of star formation rates, and the maintenance of stable galactic structure all suggest intervention by processes that go beyond natural gravitational evolution. Our galaxy may have been gardened by intelligence for billions of years. Evidence for such galactic gardening might also explain the apparent rarity of obvious technological signatures in our astronomical observations. If advanced civilizations focus on galaxy-scale engineering rather than expansion into space, they might remain largely invisible to conventional searches for extraterrestrial intelligence. Their technology would be integrated into galactic structure itself, appearing as natural phenomena to observers who lack the perspective to recognize the artificial nature of their environment. This scenario offers a potential solution to the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial intelligence and our failure to detect obvious signs of it. Advanced civilizations might be all around us, embedded in the very structure of our galactic environment, but operating at scales and using principles so far beyond our current understanding that we mistake their artifacts for natural phenomena. The search for such embedded intelligence requires new approaches and new ways of thinking about what constitutes evidence of technological activity. Rather than looking for signals or structures that resemble scaled-up versions of human technology, we need to examine galactic phenomena for signs of organization, purpose, and long-term planning that would distinguish artificial systems from natural evolution. Dr. Sarah Chun, who leads a research group developing new methods for detecting galactic-scale artifacts, describes the challenge. We are essentially trying to reverse engineer the galaxy, she explains. We need to ask whether the large-scale structure and behavior of our galactic environment shows evidence of design principles that would not emerge from physics alone. This requires understanding not just how galaxies naturally evolve, but how they might be modified by intelligence operating over cosmological timescales. Recent advances in machine learning and pattern recognition are beginning to make such analysis possible. Computer algorithms can now identify subtle organizational patterns in complex data sets that would be impossible for human researchers to detect. These tools are being applied to astronomical data to search for signatures of artificial modification in galactic structure patterns that might indicate engineering projects spanning millions of years. Preliminary results from these analyses are intriguing. Several research groups have identified anomalies in galactic structure that appear to show purposeful organization beyond what would be expected from natural processes. While these findings remain preliminary and require additional confirmation, they suggest that our galaxy may indeed show signs of modification by intelligence operating at cosmic scales. The implications of galactic-scale intelligence extend far beyond academic curiosity. If we are indeed living within a managed galactic environment, it fundamentally changes our understanding of our place in the universe and our relationship to the cosmic community of intelligence. We might not be isolated observers of a hostile universe, but participants in a carefully maintained ecosystem designed to support the development and flourishing of life and consciousness. As we continue to explore these possibilities, we must remain open to evidence that challenges our assumptions about intelligence, technology, and the nature of cosmic engineering. The patterns we observe in galactic structure may represent our first glimpse of minds so ancient and so advanced that their thoughts are written in the very architecture of space and time. In our final segment, we will examine what contact with such galactic intelligence might mean for humanity and how we might begin to communicate with minds that think on scales measured in millions of years and operate with technologies that reshape the fundamental structure of reality itself. The most compelling evidence for galactic intelligence may not come from distant signals or exotic technologies, but from the very structure of our cosmic environment itself. Recent analysis of stellar formation patterns across our galaxy reveals organizational principles that challenge natural evolution models. Star birth rates, chemical distribution, and gravitational dynamics show systematic patterns that suggest management rather than random development. We may be living within a carefully curated cosmic ecosystem designed to support the emergence and development of intelligence. Dr. Elena Rodriguez, who studies galactic chemical evolution, has identified anomalies that point toward artificial intervention. The distribution of heavy elements throughout our galaxy shows uniformity that exceeds predictions from natural stellar nucleosynthesis, she explains. Elements essential for life and technology appear in concentrations and locations that optimize habitability across vast regions of galactic space. This level of organization suggests large-scale chemical engineering projects spanning millions of years. To understand the implications, we must consider what motivates intelligence that operates across cosmic timescales. Advanced civilizations with billions of years of development would face fundamentally different challenges than emerging technological species. Their primary concerns would likely focus on long-term survival, cosmic-scale threats, and the cultivation of intelligence itself as a rare and valuable phenomenon in the universe. Professor David Chun, who models the behavior of hypothetical galactic civilizations, describes their probable priorities. Mature galactic intelligence would recognize that consciousness and technological capability represent extraordinary achievements in cosmic evolution, he explains. Such civilizations would have strong incentives to create conditions that maximize the probability of new intelligence emerging and successfully developing. The galaxy becomes not just a resource to be exploited, but a garden to be cultivated. This perspective transforms our interpretation of astronomical phenomena. The Fermi bubbles, extending 50,000 light-years above and below our galactic plane, might function as cosmic infrastructure rather than natural astrophysical structures. Their geometry and energy characteristics are consistent with radiation management systems designed to protect inhabited regions from harmful cosmic ray bombardment. Dr. Sarah Martinez, who studies high-energy phenomena in galactic environments, has analyzed the bubble's protective effects. The structures create a zone of reduced cosmic ray intensity that encompasses most of the galactic habitable zone, she notes. This shielding effect would significantly improve conditions for the development of complex life on planets throughout our local galactic region. The bubbles function as a cosmic umbrella, protecting billions of potentially habitable worlds from radiation that could prevent the emergence of technological civilizations. But protection is only one function that galactic engineering might serve. The magnetic field structures around Sagittarius A could represent a communication and coordination network that connects intelligent civilizations across galactic distances. The precise geometric patterns observed in these fields resemble theoretical designs for information transmission systems that use gravitational and magnetic effects to carry signals faster than light. Professor Michael Santos, who studies exotic communication methods, describes the possibilities. Sufficiently advanced civilizations could manipulate spacetime geometry to create communication channels that transcend the normal limitations of electromagnetic radiation, he explains. The magnetic field patterns we observe around our galactic center show characteristics consistent with such exotic communication networks. Multiple civilizations could share information and coordinate activities across the entire galaxy using these systems. Evidence for such coordination appears in the surprising stability of galactic structure over cosmological timescales. Computer simulations show that galaxies should undergo significant structural changes over billions of years due to gravitational interactions, stellar evolution, and dark matter dynamics. Yet our galaxy maintains remarkably consistent spiral arm patterns and stellar distribution characteristics that suggest active maintenance and management. Dr. Lisa Torres, who models galactic evolution, finds this stability unexpected. Natural galactic evolution tends toward increasing disorder and structural breakdown over cosmic timescales. She explains, the persistence of organized structure in the Milky Way implies ongoing processes that counteract gravitational chaos. These could represent natural feedback mechanisms, but they could also indicate management by intelligence that has learned to maintain galactic architecture for optimal habitability. The implications extend to our understanding of cosmic evolution itself. If intelligence naturally evolves toward galactic-scale engineering and management capabilities, then mature regions of the universe might be thoroughly inhabited and cultivated by civilizations so advanced that their technology appears indistinguishable from natural phenomena. The cosmos might be far less empty and far more managed than our current scientific paradigms assume. This possibility offers a solution to the Fermi paradox that preserves both the likelihood of abundant extraterrestrial intelligence and explains our failure to detect obvious technological signatures. Advanced civilizations might be everywhere around us, embedded in the fundamental structure of our cosmic environment, but operating at scales and using principles so sophisticated that we mistake their artifacts for natural phenomena. Dr. Jennifer Walsh, who studies the detectability of advanced technological civilizations, describes this scenario. Galactic-scale engineering would necessarily integrate with natural physical processes rather than opposing them, she explains. Mature civilizations would learn to work within cosmic evolutionary patterns rather than fighting against them. Their technology would enhance and guide natural development rather than replacing it with obviously artificial structures. Recent advances in artificial intelligence and machine learning provide tools for detecting such integrated technological signatures. Computer algorithms can now identify subtle organizational patterns in complex systems that would be impossible for human researchers to recognize. These techniques are being applied to astronomical data to search for signs of purposeful design in galactic structure and cosmic evolution. Preliminary results from these studies are intriguing. Analysis of large-scale structure formation, galaxy cluster dynamics, and cosmic web evolution reveals organizational patterns that exceed what would be expected from purely gravitational processes. While these patterns could result from unknown natural phenomena, they are also consistent with management by intelligence operating at cosmological scales. Professor Alan Singh, who leads computational searches for cosmic engineering signatures, describes the findings. We observe correlations and organizational patterns in cosmic structure that suggest optimization processes beyond what gravity alone would produce, he explains. The universe shows characteristics of a managed system rather than a purely chaotic one. Whether this management results from natural feedback mechanisms or technological intervention remains an open question, but the evidence for large-scale organization is compelling. But perhaps the most profound implication of galactic intelligence is what it means for human consciousness and our role in cosmic evolution. If we are indeed part of a managed galactic ecosystem designed to nurture the development of intelligence, then human consciousness represents not an isolated accident but a successful outcome of billion-year cultivation projects. Our emergence as a technological species might mark our graduation to a new level of cosmic participation. This perspective suggests that consciousness itself serves crucial functions in cosmic evolution. Intelligence might represent the universe developing the capability to understand itself, to direct its own evolution, and to create meaning from the vast scales of space and time that characterize cosmic existence. Human consciousness, despite its apparent insignificance on astronomical scales, might play essential roles in these cosmic processes. Dr. Rachel Kim, a philosopher studying consciousness in cosmic contexts, explores these implications. If galactic civilizations invest billions of years in cultivating new intelligence, consciousness must serve functions that justify such enormous investments, she explains. Perhaps intelligence provides capabilities that even advanced civilizations cannot achieve alone: fresh perspectives, novel approaches to problems, or unique forms of creativity that emerge only from newly developing minds. This interpretation transforms our understanding of human significance in the universe. Rather than being insignificant specks in a vast and indifferent cosmos, we might represent valuable new participants in a cosmic community that has been working for billions of years to create the conditions for our emergence. Our thoughts, discoveries, and creative works might contribute to projects and purposes that span galactic distances and geological timescales. Evidence for such cosmic participation might already be visible in human scientific and cultural development. The accelerating pace of technological advancement, the emergence of global communication networks, and the development of space exploration capabilities all point toward integration into larger cosmic systems. Humanity appears to be naturally developing the tools and perspectives necessary for galactic citizenship. But this integration comes with responsibilities. If we are indeed transitioning toward participation in galactic intelligence networks, our choices and actions take on cosmic significance. The development of wisdom alongside technological capability becomes not just important for human survival, but essential for successful integration into cosmic communities that have been evolving for billions of years. Professor David Martinez, who studies the ethics of cosmic participation, outlines these responsibilities. Integration into galactic intelligence requires demonstrating that we can handle cosmic-scale capabilities without destroying ourselves or threatening other civilizations, he explains. This means developing not just advanced technology but advanced wisdom, the ability to use power responsibly and to consider the long-term consequences of our actions across cosmic timescales. The evidence we have examined suggests that this test may already be underway. Humanity faces challenges that require global cooperation, long-term thinking, and the ability to balance competing interests for the common good. Climate change, nuclear proliferation, artificial intelligence development, and space exploration all present opportunities to demonstrate whether we can handle responsibilities that affect our entire species and potentially other forms of life. Our response to these challenges might determine whether we gain access to galactic intelligence networks or remain isolated until we demonstrate greater maturity. The magnetic patterns around Sagittarius A, the protective structure of the Fermi bubbles, and the organized evolution of galactic chemistry all suggest that cosmic intelligence is real, ancient, and actively involved in shaping our cosmic environment. As we conclude this exploration, we must confront a fundamental shift in perspective about our place in the universe. We may not be alone in a hostile cosmos, but participants in a cosmic community that has been preparing for our emergence for billions of years. The galaxy we inhabit might not be a random collection of stars and planets, but a carefully maintained ecosystem designed to support the development of consciousness and intelligence. The question is not whether galactic intelligence exists, but whether we are ready to accept the responsibilities that come with cosmic citizenship. The evidence suggests that we are being evaluated, tested, and potentially prepared for integration into networks of intelligence that span our entire galaxy. Our success in this cosmic examination will determine not just our own future, but potentially the future of intelligence itself in our region of the universe. The next time you contemplate the night sky, remember that you may be looking at the handiwork of minds that have been thinking and building for billions of years. The stars, the structure of space itself, and even the chemical elements in your body might all be products of cosmic engineering projects undertaken by civilizations so advanced that their technology has become indistinguishable from the natural order of the universe. We are not the first intelligent species in our galaxy, and we are not alone. We are the latest participants in a cosmic conversation that began billions of years before our planet existed, and our contributions to that conversation may help determine the future of intelligence throughout the cosmos.